Okay, thank you very much. And so, yes, it's a pleasure to be here again. So I think the first time I talked here was 2001, and also another talk in 2009 about different missions. But so it's been a while since I've talked at this place. But so we're going to be talking tonight about a rover which is going to Mars. It hasn't actually gone to Mars yet, but it'll be going in 2028. So we're working on that, and I'll tell you more about that. This is an artist's impression of the rover on the right-hand side here. And that's an artist's impression because it hasn't landed yet. It's a 300 kilogram rover. And up the road in Holmbury St Mary, we're leading the camera system. That's PanCam, which is at the top of the mast here. And we're also now building the infrared spectrometer, which is associated or works very closely with PanCam. And we're building part of that at the moment as well. So we've delivered the camera, and I'll tell you more about the mission. But also looking more generally at looking for life on Mars and other places, because there are interesting places in the solar system where either there could have been, like in the case of Mars, or maybe even could be life now. And yes, as was mentioned, I'm Deputy Director in charge of the solar system. And just to clarify that a bit, is in charge of solar system research at Mullard Space Science Lab. The other Deputy Director is in charge of the rest of the universe, astrophysics. So between us, we have it covered, but I deal with our local solar system, and that's where we live, so it's important to us. Okay, and we're going to be talking about a few of the Mars missions. So just starting off with where in the solar system could there potentially either be or have been life, bearing in mind the only life we know of at the moment that's been proved is here on Earth. No life found elsewhere yet. But Mars is one possibility. That's what we're mainly talking about tonight. And the size of this is about half the size of the Earth. That's very important because in the solar system's history, the solar system is 4.6 billion years old or so. So when Mars formed and the rest of the planets formed, Mars was smaller than the Earth. So it means that its heat of formation took longer to actually escape from the Earth than it does of Mars. Mars is smaller, so it loses its heat of formation more quickly than Earth does, and that means that it loses its magnetic field about 3.8 to 4 billion years ago, because the core basically stops moving, and so no magnetic field now on Mars, but the signs of crustal magnetic fields, which are the evidence for there having been a magnetic field on Mars. So Mars is an interesting location, and it's one of the places, and of course relatively near to us, but still a long way away. It's 1.5 times our distance from the Sun, so it takes a little while to get there. Anyway, Mars is an important thing for exploration. So there are other places in the solar system, though, which also could be relevant when we're talking about could there be life elsewhere. So Europa, one of the moons of Jupiter, is one of these. In size-wise, this is much smaller than the Earth. It's an icy object, but underneath that icy crust, it's ice you can see there. Underneath the icy crust, there's a liquid water ocean, it seems, from data. The data all seem to point towards a liquid water ocean on Europa, with actually more water than we have on the Earth. So it's a really interesting location. And that water ocean, in the case of Europa, is in contact with rock, silicates. So not as at Ganymede and Callisto, there it's in contact with ice at the bottom of the ocean. In the case of Europa, it's in contact with silicates, and basically, the ocean bed is rock. And so that means that Europa in the Jupiter system is one of the more habitable, well, the most habitable moon potentially. So we have a mission called JUICE, which is on its way to Jupiter, and to look at the moons and as well as Jupiter itself. And the US also has the Europa Clipper, which is going to do lots of flybys of Europa. So with JUICE, we will do a couple of flybys of Europa, but that will actually do flybys also of Callisto and Ganymede before going into orbit around Ganymede. So it does this, arrives in the Jupiter system in 2031, does some flybys, goes into orbit around Ganymede in 2034. Ganymede has its own magnetic field, so that's a really interesting moon in the Jupiter system. But Europa is the one where there could potentially even be life. So with that mission and Europa Clipper, those are looking at habitability. You know, could it potentially be habitable? Won't be searching for life, but it's searching for habitability. Another place here, Enceladus, one of the moons of Saturn, which has some amazing features. So a few years ago, we were enrolled in the Cassini-Huygens mission, which went to the Saturn system and did flybys of Titan and Enceladus. And early on in the mission, something interesting in the magnetometer data, the magnetometer led by Imperial, Michel Doherty is the PI of that, principal investigator of that instrument. But they discovered with magnetic fluctuations that there seemed to be some sort of atmospheric type thing. And what this turned out to be with the imaging was plumes of water coming away again from a subsurface ocean. From these sort of bluish looking features here at the south pole of Enceladus, these are tiger stripes, the so-called tiger stripes as they were called by the mission people. Otherwise a very bright object, but again, a liquid water ocean. And so we were able to change the mission to actually fly through those plumes again and again. So we had something like 20 flybys of Enceladus through the plumes. And with that actually flying through the plumes, we were able to actually fly through material from this subsurface liquid ocean underneath the surface of Enceladus. So, and one of the things that was found in that was indeed silicates. And so again, that's evidence that the ocean floor is silicates and rock, that type of thing. And again, this brings Enceladus into the conversation about habitability as well. So Enceladus, as a result of the Cassini mission, really, we think that the right conditions there for perhaps life to even be there now. That's the case with Europa as well. So these are really the top three in terms of likelihood for potential life elsewhere. Mars probably a while ago, but we'll get to that and why. But Enceladus and Europa potentially now. So the European Space Agency are now working on proposals for a mission to Enceladus, which would be leaving another one, which will be leaving in or launched in about 2040, arriving in about 2055. So those of us that are still here and able to look will, I'll be wheeling in and seeing how the people who are currently the students actually that we're working with, who are developing the instruments, which hopefully will go on that mission. So that's really exciting. Return to Enceladus, and it's one of the top locations potentially for life elsewhere. Titan was another target of the Cassini mission, of course, and we used Titan time and time again to actually change the orbit of Cassini as it was going around Saturn, and sort of change the inclination of the orbit and change the angles and so on. But Titan, of course, a fascinating moon in itself. It's the only moon in the solar system which has a significant atmosphere, and that is a nitrogen and methane atmosphere. So very interesting. You can see the haze around Titan here. This is an image from Cassini, which is able to penetrate down to the surface using ultraviolet and infrared, and putting that together, you can actually see all these the surface features, but also the haze. So that haze at Titan is very interesting. We have prebiotic chemistry going on there as well. So with our instrument actually developed, only a few miles from here, we were able to find very large negative ions, which are potentially carbon chains and potentially rings as well. So those are the signs that those are prebiotic chemistry going on. So we don't have life on Titan. Titan is too cold for that. It's too far away from the sun. And we're talking about on the surface, whereas these are subsurface in the oceans. There's the possibility of life there. So another object here, Venus. So a few years ago, there were indications of phosphine in the atmosphere of Venus, and phosphorus is one of the things you need for life. So that was interesting, but those results are controversial, and some follow-on measurements have shown that there's no phosphine there, and I think probably the jury is out as to whether there are or not. Venus is a very hostile place, nearer to the sun than us. It doesn't rotate very quickly. It has a runaway greenhouse effect going on. I think you'll be hearing more about Venus later on in this series of the Mole Valley Geological Society. So you'll be having a lecture about Venus then. But in the atmosphere of Venus, this is where the possibility of life perhaps is. So this is at the cloud level of Venus. You can see the clouds here. We have a very slowly rotating planet, but super rotating atmosphere. So you get this V shape in the clouds, very fast winds going around the equator. But what we're seeing is sulfuric acid clouds. There is some water in there, so there is the possibility, but it's not very likely because of the hostile environment there that there would be life. But so it's got a question mark there. Also, extrasolar planets. Of course, we can use our own solar system planets as good places to start. But we're now discovering many more extrasolar planets, and so missions which are coming up. So, for example, Plato is launching later this year, a European Space Agency mission. Our lab has played a big role in that as well. It's one of the biggest cameras to be sent to space. It will be looking at extrasolar planets and looking at using the transit method. And then later on this decade, we have the launch of Ariel, which will be looking at extrasolar planet atmospheres and looking at their composition. And so that gives us a good step towards looking for, do we have the ingredients for life there too? But in our own solar system, this is a good place to start because we can send probes there and do the work that we need to. So why are we interested in Mars? So 3.8 billion years ago on Mars, it looks perhaps, and this is an artist's impression, not a model, but the computer models and the data shows that at that time there could have been, well, there's certainly a more intense atmosphere. This was because before the magnetic field was lost. That it may have been covered with water, at least some of it, and so there's evidence for that from the various missions which have gone more recently. You can see clouds in the atmosphere and ice caps. So 3.8 billion years ago, it's an environment a little bit like the terrestrial environment, and of course, that time, about 3.8 to 4 billion years ago, is when life was starting on Earth. So our oldest known life on Earth, about 3.9 billion years old. And so it's about the same time as life was starting on Earth. So possibly life might have started on Mars at that time. And that's why we're sending the missions. Because Mars now, on the right-hand side, because of losing that magnetic field, that means that the sun and the solar wind can strip away the atmosphere of Mars over 3.8 billion years. And so we now have a very, very low pressure atmosphere and a sort of desert-like surface, which close up has interesting colors associated with it. But overall, this red planet with iron oxides and so on the surface, very large geological features like the Valles Marineris here, large volcanoes, Olympus Mons, the biggest volcano in the solar system, and other large volcanoes. So we have Mars now, a very inhospitable place because of that thin atmosphere. So the thin atmosphere means that ultraviolet from the sun can bathe the whole planet, really. It's like being under a very intense ozone hole all the time, everywhere on the surface of Mars. Also, radiation from the sun and the galaxy can get through to the surface, and so the surface really is not habitable. It's also very cold because of that thin atmosphere. So on a good day on Mars, it's maybe 0 to 20 degrees centigrade, but at night down to minus 100 to minus 120 degrees. So every night going down to that very low temperature. So anything we land on the surface has to survive that intense temperature change. But of course, it means that life on the surface now is very, very unlikely. So Mars, 3.8 billion years ago, that was that's why we're looking for evidence of past life on Mars rather than current life. So how do we know all this? Well, the evidence from the spacecraft which we've had already. So there's lots of evidence of water on the surface of Mars. This started in the 70s with the Viking mission, which did some imagery of the surface as well as other measurements. And there's lots of evidence of water on the surface of Mars, this is an image from Mars Express, which shows one of the outflow channels of water. Again, this is 3.8 to 4 billion years ago is the time that we might have had water on the surface. But there's still the evidence there for water carving the surface. So the evidence for the magnetic field, the first time that a magnetometer, something which measures the magnetic field, was sent to Mars was the early 2000s. This paper is in 2001. This is the first sort of magnetic map of Mars, and this is a few hundred kilometers above the surface. And we can see this is superimposed on this colored map in the background. So this is longitude and latitude here. The colored map shows height on the surface of Mars, height of the terrain from the Mars Orbiter Laser Altimeter. And superimposed onto that are the magnetic field measurements. So we have dark or black and white contours here. These are little cusps of magnetic field from crustal magnetic field, which was left over from Mars. Used to have a dynamo, that magnetized, forming rocks on the surface, and that produces these remnant magnetic fields. There are also remnant or crustal magnetic fields on the Moon as well. They're less intense than they are on Mars, but that again shows that the Moon might have had an interesting history. But with Mars, this was the first evidence that Mars once had a magnetic field. So again, that would have protected the surface, not only the atmosphere being thicker at that time, but also we have the protection by a global magnetic field of Mars. And this is the evidence, the sort of remaining evidence for that global field is the fact that we have these crustal magnetic fields, or magnetic anomalies as they were initially called. So Mars, 3.8 billion years ago, it had water on the surface, it had a magnetic field, and it also had volcanism going on. So I mentioned Olympus Mons, the biggest volcano in the solar system. This is an image of it. The height of this is 3 times the height of Mount Everest. And so a very large volcano, biggest in the solar system, as I say, but of course extinct. Volcanism, though, at that time would have provided the sort of same cycle that we have on Earth with volcanism and so on. Okay, so what do we need for life? So the 4 things which we really need. So there's liquid water is important for life as we know it. We need the essential elements, so carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. That's why that phosphine measurement at Venus was interesting, because that's the phosphorus there. The other things are there too. We need a source of heat to drive the chemical reactions which eventually produce life, and enough time for life to develop. So that's the sort of recipe for life, if you like, that we have these 4 things. And so we think that was there on Mars 3.8 billion years ago, and that's why we're interested in going back with our current rovers. So what missions are we sending to Mars? So you have opportunities to launch to Mars about every 2 years because of the way the planets line up. Mars's year is about twice the Earth year. And so about every 2 years, just over, you have opportunities to launch to Mars. So in 2020, we had several missions to launch to Mars. So the UAE had the HOPE orbiter. This is a big collaboration with the US, but the UAE provided the personnel to actually do this, and a lot of the engineering associated with it. So that's looking at the Mars atmosphere and has found some very interesting things about the atmospheric composition, and of course looking at aurora as well. They've been able to do that around these magnetic anomalies, which is very interesting. China had the Tianwen-1 orbiter and also the Zhurong rover, which landed correctly first time on Mars and sent back some really interesting results, especially about the dichotomy on Mars between the sort of low northern hemisphere plains and the higher terrain in the southern hemisphere. So there's some interesting results about that. And NASA, of course, sent the Perseverance rover, which is on the surface. And I think you've had to talk about that here before from Sanjeev Gupta, who works on that significantly. And they also had the Ingenuity helicopter. So these were all sent in 2020, landed in 2021. So that's a very exciting time on Mars. And then at the end of last year, or October last year, NASA launched the ESCAPADE mission. That's going to be looking at the solar wind interaction with Mars now, looking at the escape process in more detail. And we use that to try and extrapolate back further. The MAVEN and Mars Express mission have worked with that as well, but extrapolating back to what Mars's atmosphere used to be like. Later this year, Japan will be launching the MMX mission. So this is planned for launch, I think in October or something. This is a mission which would bring back samples, not from Mars itself, but from Phobos, one of the moons of Mars. And there may be some bits of Mars in those samples, which would be interesting when that gets back. And then in 2028 is our Rosalind Franklin mission. So again, the artist's impression here, and that is of it on the surface. So, I mean, Mars is a busy place with lots of missions. So Mars Odyssey, Mars Express, Mars Reconnaissance Orbiter, Curiosity still going. I'm sure Sanji would have talked about that as well. And then we have the ExoMars Trace Gas Orbiter, sending back information about gases in the atmosphere. So our mission, the Rosalind Franklin mission, the key new thing about that is drilling up to 2 meters underneath the surface of Mars, which for some geologists here I know is not very impressive, but compared to the type of thing we can do on Earth. But on Mars, that would be the first time drilling to anything beyond a few centimeters, because the current missions like Perseverance and Curiosity can drill 6.6 centimeters into a rock or whatever to look at their samples. We'll be drilling 2 meters, so we get better or more pristine samples from underneath the surface. I'll talk about that more later. So this is a selfie image of Perseverance on the surface. And again, I'm sure Sanji would have showed something like this. So this is the camera on the top of the mast cam Z. There's also a camera called SuperCam. This is very well instrumented. It's a 1-ton rover. So it weighed, basically, I think it was compared to a Mini Cooper or something like that at the time. It's about that mass. This is the Ingenuity helicopter. And the way this was produced, obviously, was to use the robotic arm and the cameras on that to be able to build up this selfie. And you can see how the mast moves there. Also, I mentioned the helicopter, and this was the first flight of the helicopter, which is shown here. So this is the helicopter on the surface. You can see the rotors powering up, eventually getting to 2,400 RPM with counter-rotating blades to actually lift the thing off the surface for the first time that this has been done in a powered, controlled fashion on another planet. This was the very first flight with the images taken from the movie taken from Mastcam Z on the rover. This is the helicopter. And so this opens up sort of future exploration. You can actually do helicopters on the surface of Mars, even with that very thin atmosphere. It's less than 1% of the Earth's atmospheric pressure, so it's difficult to fly anything, but showing that is possible. So that opens up that as a possibility for future exploration. Okay, so as of yesterday, the rover had travelled, this Perseverance rover had travelled 43 kilometers on the surface of Mars. So this is maps from the data which is behind that, images of the surface. So it landed in Jezero crater, which is on this scale is a very large crater. So this is the crater rim here, and it landed on towards the middle of this crater. And this was an interesting place to land. It's towards the dichotomy region again, but there's a river channel going into this, which you can see the delta structure here. And there was also a river going out back in 3.8 to 4 billion years ago. And so this is the evidence for the delta. There's evidence for water flow out to the other side as well. So this is where Perseverance landed, and these are where it has taken samples along the route. And as Sanjeev would have talked about, I mean, getting these samples and deciding which samples to get is a process involving very intense scientific discussions about which samples shall we get, because the hope is eventually that these samples may be sent back to Earth, but we'll get to that in a minute. So these are some of the statistics about that. So something like 20 samples so far. Some of these have been cached on the surface, some are still on the rover. Of course, results have been sent back as well. And at the moment, the mission to actually retrieve these samples is a victim of budget cuts in the US. So at the moment, this is not going to be returned, but we'll see what actually happens. But they have had some fantastic results, and this is one of them. So this is a Nature paper from September last year, which showed, which is at a particular location, which may even indicate a biosignature on Mars. It's not proved, and I think somebody compared this on a scale of 1 to 7 of whether it's likely to be life. It's maybe 1, you know. So it's not proved by any means. But nevertheless, there are features in this in just this image which show, you know, you would need, or one way of producing this may be the presence of life. These are so-called leopard spot features. We can see this on the left-hand side here, and also poppy seeds. Not actual poppy seeds, but they look a bit like that. So the sort of black features are the poppy seeds, and then leopard spots are black areas surrounding regions where there's iron phosphate and sulfide minerals. And one of the ways you could get that combination is life, but it's not proof, as I say. So more analysis needed, I've put on here, but actually what we need to do is get that sample back to Earth to actually do that analysis. And so how that was going to be done is shown on the right-hand side here. This is images from Perseverance landing on the surface. This is one of the samples, the first sample which was taken actually. And it was hoped that this complicated series of missions would bring back the samples which are cached in those tubes like this to Earth. But that would involve 2 launches, an Earth return orbiter, which is this one, and a sample retrieval lander, which is this. But it ended up being very expensive in the US, and so unlikely now to happen because of budget cuts, unfortunately. But hopefully those samples might be returned to Earth, because it would be really interesting to look at that sample in particular, the one that I've mentioned. Which brings us on to Rosalind Franklin. So with this is planned to go in 2028. So this is the rover itself. We can see, again, this is PanCam on the top of the mast. You can see these are the solar panels on the surface. It's a solar-powered rover. The 6 wheels. We have wheel walking, so you can get around rocks and so on. This is the drill at the front of the rover, which allows us to drill up to 2 meters underneath the surface. So we have a system of rods which are put together to actually allow the thing to actually drill up to 2 meters. So the idea is you get a sample, put it in the analytical drawer, as was shown in the animation, and then analyze the samples. So the plan is to launch this in 2028. And this is now a mission with NASA again. This mission has been a roller coaster ride, I have to say. We wrote the proposal for this instrument, the PanCam, in 2003. So 23 years ago now, and we still haven't got to Mars, because initially it was going to be a Europe only mission. Then it was going to be Europe and America, Europe and NASA. NASA had to pull out because of budgetary problems. So we went with Russia. So it was going to be European Space Agency and Russia. At the end of the week in which we did the camera calibrations, and they were just starting to pack up to send it to the Russian launch site, the invasion of Ukraine happened. So we had to stop. The nations in the European Space Agency didn't want to work with Russia, very understandably. And that also means that we had to change the infrared spectrometer, which was Russian, and that actually now is being built by the UK. So the UK provided the money and the sort of technical know-how to be able to do this. So as I say, we're involved in that and building part of it. But my colleague Matt Gunn at Aberystwyth University is the principal investigator for that. So as I say, I lead the PanCam team, and it's a big team. You know, lots of institutes involved. It's not just us. But and why do we call it Rosalind Franklin? It's after, of course, Rosalind Franklin, who was an amazing X-ray crystallographer. She took this this photograph, photo 51, of a fiber of DNA using X-ray diffraction, and this was critical to the Watson and Crick discovery of the double helix. And they went on to do that. They got the Nobel Prize for it. Unfortunately, Rosalind Franklin had passed away by that time, and so was not able to share in that. But she did lots of other important work on the structure of carbon and viruses and so on. And so it's very appropriate that we call the rover after Rosalind Franklin, because we're looking for life on Mars. So, and of course, DNA very important in life on Earth. So why do we need to drill deep? So this is a sort of artist's impression of the rover on the surface, and we have an outcrop maybe, and some dust and regolith on the surface, and we need to drill up to 2 meters. We need to get underneath where the ultraviolet radiation which bathes the planet, where that can penetrate to. That's about 1 millimeter. There's various oxidants, things like oxidants in the surface, which penetrate to about 1 meter, and then about 1.5 meters we need to actually to filter out the radiation coming from space. And so we have much more pristine material if we can drill more than 1.5 meters. So drilling 2 meters is really important for us to do that. And so this is the unique thing about this mission, and why we're still, after 23 years, trying to get this thing to Mars, because it's the first and only mission which, with a deep drill, to be able to actually do this work. So that would be it, drilling into the subsurface. So that's our strategy. So our landing site is Oxyoplanum, which is, this again is the image of Mars here with the height map onto the globe here. So this is the Oxyoplanum area. We can see again, this is at the boundary between the sort of low regions here, which are the blue ones, going through medium elevation up to high elevation, which is the red here. This might have been a beach 3.8 to 4 billion years ago, if there was an ocean in the northern hemisphere, which the Zhurong results seem to indicate that there might well have been water coverage for a long time in the region where they landed, which was a little bit further north. So that's interesting. But there was certainly water involved in this region. From the orbiters, we can see phyllosilicates, so clays on the surface of Mars in this region, and many others around the equator, including Jezero crater, where Perseverance landed. So that's evidence for water having been involved on the surface at some point in the past. And so this is the landing site here. So they're definitely clay-bearing rocks, about 4 billion years old, and there's remnants of a fan or delta in this region coming from this Cocoon Vallis area, and so we're landing near that delta. So again, material would have been, as with the case of Perseverance, material would have been collected from a large area and brought down by water through into this region, through this outflow channel, and then potentially into the ocean. So it's a good place to land to look for possible signs of life. So this is the payload on the. These are the instruments on the rover. So on the left-hand side, we can see the context instruments, as we call them. These are the ones which help us to decide where to drill. So we have PanCam. So as I say, this is the one which we are leading from Mullard Space Science Lab, UCL, just up the road. That's PanCam. We now have the infrared spectrometer called ENVIS. So the UK Space Agency did really well to add this to the payload, and it means our teams are working really closely together, because of course we can do a certain amount in the visible and very near infrared, But going deeper into the infrared, we really need to do to get better mineralogy than we can with just visible. And so these really are the main two instruments which will be able to look from a distance at what the composition is on the surface. Wisdom actually looks underneath the surface. This is a subsurface sounding radar and looking for ice underneath the surface and also where outcrops of rock are, and again helping to search for good drilling sites, but using the third dimension underneath the surface. There is also a close-up imager, so on the tip of the drill there's a camera which allows us to look very close up at things like the drill tailings and the material actually near to the rover. In the drill itself, we have a little instrument, a visible and near infrared spectrometer called MARMIS. And so that is able to get the geology from, if we're drilling 2 meters underneath the surface, we may have different conditions than we do on the surface. And so that's able to get the local geology from where we actually get the samples from. When we get the samples, these are put into the analytical drawer and analyzed by these analytical instruments. So we have micrometer, which is a visible and infrared spectrometer, again looking at images of the samples from underneath the surface. There's a Raman spectrometer, which we use a laser to and then look at what is coming back from that, and that can help with mineralogy as well. And then the Mars Organics Mass Analyzer, and this is why NASA is still interested in this mission, because they have a big involvement in this instrument. So the Mars Organics Mass Analyzer, this is a gas chromatograph mass spectrometer. So the idea is we have bits of the samples are heated up to very high temperatures. We analyze the composition using a mass spectrometer and look at the composition of the material. And this is the first time this will have been done. It also looks at chirality, so left-handed and right-handed molecules. For those of you who remember chemistry and biology, there's left-handed molecules and right-handed molecules. Some are important for life and some not. There's left-handed and right-handed sugars and so on. So this chirality, this is the first time this will have been done on Mars. And so this helps us to understand the importance of that for life potentially on Mars. Okay, so a bit about our own instruments. So the PanCam, so as I say, I'm the lead of this, but we're working with a big team, and I must stress that there's lots of institutions involved internationally, but the UK leading it and playing a huge role in the software and so on, which is needed for this, as well as delivering the instrument to the rover. Inside, we have two wide-angle cameras, as they're called, at the ends of this optical bench that we have. And so these are separated by 50 centimeters. So we get, with that really good stereo reconstruction, a few meters away from the rover. That's why we have that wide separation. Each of them also has a little filter wheel, and that's illustrated here in our moving logo. So the idea is we have 11 filters in each of the two wide-angle cameras in front of them. So it's basically a black and white camera, but with filters in front. And so with that, we can do geology and atmospheric science with that combination of filters which we have designed. Those are the actual filters shown there. And those are the ones which will be looking at the surface of Mars. We also have a high-resolution camera that's shown here. So the light comes in here. There's a mirror, a focusing mechanism, and a focal plane here. So it's a longer length, so we can get better resolution images of particular rocks. So this is the geologist's dream, to actually have that combination of wide-angle stereo composition from the visible and then the high-resolution camera able to look close and look at textures and so on, and then combining that with NVIS, which is looking at the infrared in one particular spot of the high-resolution camera field of view. So the infrared spectrometer, so again, as I say, this was replacing a Russian instrument. So the UK stepped in and funded this, which was great, because it means that we can do the proper mission that we needed to do. So this covers 0.9 to 3.2 microns, and this is some of the details of what's happening. But Aberystwyth University and Matt Gunn is the lead of this. We're building the optical box, so the actual sensor system here at, again, just up the road, using our experience from PanCam and getting that ready for a really challenging environment on Mars. I mentioned the temperature, but also we have to worry about radiation, operation in a vacuum, etc., etc. So, you can use that experience. RAL Space are involved in the electronics box, and then some industrial companies involved in the optics and the coatings being used for this. So this combination of PanCam and ENVIS is very powerful for looking at the mineralogy. So this was taken a few years ago with PanCam on the rover. This is the old Russian instrument which we're now replacing. This is the boom which PanCam sits on. This is the drill on the front, and this is the actual flight rover. And to give you an idea, the thing is 2 meters high, so it's a bit taller than me, is where the camera will be, so looking down like that. As I say, it's about 300 kilograms, so more like golf buggy size of the rover. This is an image of PanCam in our clean room. We have to be very careful in the construction and putting this together to actually make sure that we're not taking life from Earth to Mars and measuring that, but instead looking at any life from Mars. So we have to do this in very clean conditions, as well as do lots of testing to make sure it's going to survive. The mechanisms are okay at the temperature and so on. And then we have a calibration target here, and fiducial markers, and then a rover inspection mirror, which this is all part of the PanCam system. So it's not just a camera, it's a really smart camera which is able to look at the mineralogy and atmospheric science as well. So this is a bigger picture of the actual filters. So we have 11 on each of the 2 wide-angle cameras. So most of these are geological filters. There are a few solar filters as well. So the very narrow bandwidth here. So this is the first number is the wavelength, the center wavelength, and then the other number is the width in nanometers of the light that you let through. So the solar filters, this allows you to look, for example, at sunset on Mars and look at the amount of water vapor in the atmosphere on Mars. So that's one of the measurements that we're looking forward to. But the geological filters have been very carefully designed to get as good as possible. We can't do everything with just visible, as I say, but as good as possible mineral identification. But then with the addition of ENVIS, we have really good, better mineral identification than we can just with PanCam. But also we can do these atmospheric measurements, as I say. With the high resolution camera, we can provide the rock texture. So it's a very powerful camera system going to Mars. So this has been tested in a number of different environments. So this is the so-called PanCam emulator. So Aberystwyth University built this actually, and it's been to the field a number of different times. I think this particular one is Iceland somewhere. So, very interesting for geology, and some aspects, some places on Iceland have very good, good Mars analogues. This one is the Atacama Desert in Chile. Again, another good analog site for looking at this. And so this has been around the world to different sites to test really the team and also the technical, how the camera is actually working. And there's a number of different things which you can do. So obviously producing the 3D elevation map is one thing you can do. And then the geologists on these sedimentary areas added dip and strike, and so you can look at the sedimentology there. You can also look at composition using those filters, and so this is principal component analysis, as it's called. And so these are ratios of the amount of signal in the different filters, and that allows you to separate some of the minerals here. This was done, this particular one was from an Iceland expedition. And then the right-hand side one here, this is the filter, the spectrum in the visible for a particular location in the Atacama Desert. So this works very well on the rover. This was the first time we integrated back in 2019 now. So it's all with the rover and ready to go, and we're just hoping that it finally does. This was actually, I forgot to mention this, but Airbus in Stevenage built the rover. So this is why the UK is so interested in getting this to Mars, because the UK built the rover, but also we have these big academic involvements with ourselves and other groups involved in the PanCam, and similarly with ENVIS now as well. And also we have an involvement in the Raman spectrometer, so Leicester University and Rutherford Appleton Lab are involved in that. So we have that great combination of UK expertise on the mission, which is doing it. But this was the first time we integrated it, PanCam, on the mast itself in Stevenage. And this is a colleague actually holding up a piece of paper here in front of the camera. Bearing in mind, this is the first time it's being tested on the rover. And what it says is "Hello Mars." Okay, so for those at the back, so this was our first light image on the rover itself, taken in August 2019. So we've had to make a few little changes since then. So just last year we made a change to make sure that the solar filters will work once they get there. There's other tests which are going on at the moment. This one is in a Mars yard in Turin. So this is Thales Alenia, the industrial company which were the lead for the entire mission. Airbus in Stevenage did the rover, were the lead for the rover, but the actual spacecraft and the whole mission is done with Thales Alenia. And this is a model, sort of the engineering model of the rover with our engineering model camera on the tip here. So this is not something which is flying, but this is being done to do things like testing operations and testing how the drilling works, things like that. This is PanCam on the top of the mast with the old Russian instrument, and so I'm looking forward to getting the picture with the new UK version of this actually on the top of the mast, the flight model. So that should happen later this year. So our engineering teams at the moment are very busy putting together the ENVIS to replace this ICEM instrument. But this is the rover being tested. You can see it's got some ropes here. This is to try and simulate the Martian gravity, which is about a third of that of Earth, because we're doing drilling tests, and so to drill with, you know, it goes some way to simulating the environment on Mars. And this is a I don't know if that's going to work or not, but it's a flyover. Yeah, it is actually. So this is shows the three-dimensional capability of PanCam. This is a flyover of the digital terrain model, which is being built as a result of those two images, which we then put together, and it gives you an idea of the resolution we will get. Each of these bars is 1 meter with 10 centimeter graduations on the surface, so you get an idea how good the stereo reconstruction is from PanCam, and that's done in the Mars yard. There's some drilling tests were done on the rover, on the Amalia rover. This is the spare, as I say, this is the ground test model, as they call it, to actually, so it's not the flight rover. But here's the drilling going on. You can see the drill tailings, and so obviously there's information you can get from that, from Clupy, the close-up imager. And this is the sample draw. So a sample was actually retrieved from underneath the surface, a core sample retrieved from underneath the surface, put into the analytical drawer, and then now you see it, now you don't. That's the idea of this animation. And this is imaged actually with a high-resolution camera on PanCam. So it shows the system all works very nicely. This is a video which I hope will work. So this shows the mission and how it will land on Mars. So it says in 2028, ESA will launch its most ambitious exploration mission. So it's the first time Europe hopefully will have landed successfully on Mars, fingers crossed, to search for signs of life. So that's the heat shield which protects the entire thing as we go into the atmosphere. The parachute which deploys, as with Perseverance. We once we've landed, start looking at the surface. This is a bit of an animation which shows speeded up very quickly. We found out the other day that actually will take a few days for each drill to be done. So a very exciting mission. So we're looking with the ESA Rosalind Franklin mission for signs of life on Mars. So just to finish off, join us on this journey, it says. So here we are. Okay, so we're doing various mission simulations. The last one actually was held in November 2024. But this year, in October, we're going to do a field test somewhere in Spain to actually have the rover there and do another test, but this time with all the instruments present. We, in the past, have done them with subsets of the instruments. But the idea is we will be able to do that. But this shows the operation center in Turin and the types of tools which we have to look at the data. We're building new tools at the moment now as well to help with this. And just as a summary, so Hope, Tianwen-1 and Zhurong, Perseverance and Ingenuity, all these arrived in 2021. And the samples, which are about 6 centimeters, these are cached, hopefully for Mars sample return. So hopefully one day that mission will go to actually bring those samples back, because of course the measurements you can do on Earth are much more accurate than the ones that you can potentially do with the instrumentation which they have on the on that rover. But actually this decade, our rover, the Rosalind Franklin Rover, will be launched to provide a really important new dimension on Mars. It's the only rover to be doing this. We're drilling 2 meters underneath the surface. And so at our lab, we're leading PanCam and also helping to build NVIS. So I think I will stop there. Thank you very much, and see if there's any questions.